In section 4.6, we're going to be looking at solving linear inequalities in two variables. So up to now, we've solved linear inequalities in one variable, and you guys represented those solution sets as either the inequality, where the variable was by itself on one side of the inequality, and then also in interval notation and also graphically. And then we have also looked at graphing linear equations. So we just studied the different forms of the equation of a line and graphed those. And now we're going to be looking at representing the solution sets for linear inequalities in two variables. So we're kind of taking skills that we've done, or skills that we've used and concepts that we've learned in the previous two chapters, and we're putting those together to help us in this section. Okay, so solutions to linear inequalities. So let's think back. Linear equations with two variables. So like why we looked at the different forms of the equation of the line. But whenever you graph a linear equation, the graph is a line. And the solutions to any linear equation means there's an equal sign, are going to be points that would lie on the graph of the line. So any ordered pair that would represent a point on the line would end up satisfying the equation. A linear inequality with two variables. So inequality, remember those symbols. So less than, greater than, less than or equal to, greater than or equal to. So a linear inequality with two variables has a solution set consisting of a region that defines a half plane. So linear equations have infinitely many solutions because it's any point that lies on the line. Linear inequalities also, well, they end up having usually infinitely many solutions as well. They can also have no solutions, but we'll talk about that more later. But the solution set ends up consisting of half of a plane, like half of an XY plane. So I have an example here. This linear equation and linear inequality look very similar. For the linear equation, it's a line with a slope of 3/2 and a y-intercept of 0,3. And then the linear inequality has a boundary line that ends up being the same as the linear equation. So the boundary line has a slope of 3/2 and a y-intercept of 0,3. But then notice that it also has the shaded region. So the shaded region represents all of the ordered pairs. So any ordered pair that lies in that shaded region is going to end up satisfying this linear inequality. So this graph, whereas like linear inequalities with one variable, we graph the solution set on a number line. Now when there's two variables, we can represent the solution set in the XY plane, so in two dimensions. Okay, so for the inequality, the line defines one boundary of the region that is shaded. This indicates that any ordered pair that is in the shaded region, including the boundary line, will satisfy the inequality. In this case, sometimes the boundary line is not included, and we'll look at what happens when it's not. So like we can choose a few test points to substitute them into the inequality to determine whether or not the ordered pair is part of the solution set to this inequality. So like if I choose the point 4,2 to test. So I'm substituting 2 in for y and 4 in for x. Oops. Okay. I simplify the right-hand side. That'll be 6 plus 3. We get 2 is less than or equal to 9. Well, that's a true statement. Okay. Therefore, the ordered pair 4,2 is part of the solution set to this inequality. Okay, if I choose, let me switch colors just to differentiate. Okay, so if I choose another point, how about -3,5? Okay, well, if I substitute 5 in for y, 3. So negative 9/2 plus 3. Okay, so that'll be negative 3/2. Right, negative 9/2, that would be plus 6/2. 3 can be thought of as 6/2. Gives us negative 3/2. Well, negative 3/2 is not greater than or equal to 5. That's a false statement. And this is the same inequality as above. So if we go back up to the graph up here, we can see that the point 4, 2, we would have to extend the graph, huh? So that's 3, let's say this is 4. 4, 2 would be up here, and it would be in the shaded region, right? If we imagine this graph extending in all directions, the point 4, 2 would be in that shaded region, so it would be part of the solution set. Whereas the point negative 3, 5 we can see is not in the shaded region and therefore not part of the solution set to this linear inequality. Okay, but 4, 2 is part of the solution set. Okay. So the graph of the solution set to a linear inequality is always going to be a region or a half plane. Right? XY plane, you can think of any line extending in both directions with a line of any slope. Extending in both directions, it's going to cut the plane, the XY plane, in half, and therefore we call the solution set, that shaded area or shaded region for the linear inequality, a half plane. Okay. So however, the boundary may not always, and I mentioned this before, the boundary line may not always be included. So we have two inequalities that look very similar here. The difference is this first inequality reads as y is strictly less than 3/2 x plus 3. And then this other one reads y is less than or equal to 3/2 x plus 3. Okay, so for the first one, when we have y is strictly less than 3/2 x plus 3, it means that the boundary line is not included. So points that lie on the boundary line are not actually part of the solution set. And we indicate this whenever we represent the solution set in a graphically in the XY plane. We represent this as a dashed line usually. And you can see if we pick a point that lies on the boundary line, so like 0, 3, if we try substituting 0, 3 into this inequality, we would get 3 is strictly greater than 3, which is false. That's not a true statement. Okay, so 0, 3 is not part of the solution set. And you'll get a false statement with any point that lies on the boundary line in this case. Whereas over here, if we pick that same point, 0, 3, and substitute in 3 for y, 0 for x, we get 3 is less than or equal to 3, which is actually a true statement. Okay, so points that lie on the boundary line for this inequality are going to be considered part of the solution set, and we call that an inclusive boundary. Okay, so if it's strictly less than or strictly greater than, you used a dashed line to represent the fact that the boundary line is not included in the solution set. But if it's greater than or equal to or less than or equal to, then you do a solid boundary line to represent the fact that the points that lie on the boundary line would be part of the solution set. So how do you determine where to shade? There's two methods. So I want you to first determine whether to shade above or below the boundary line, and sometimes it ends up being to the left or the right, and we'll talk about that in a couple minutes. But you determine whether you shade above or below the boundary line after you've gotten y by itself on one side of the inequality. If y is greater than, so greater than or equal to or greater than the rest of the inequality, then you end up shading above the boundary line. So you can see all of this is shaded. Okay, and then if y is less than or equal to the rest of the inequality, then you end up shading below the boundary line. Okay. You can always double check using a test point. And it depends on what your goal is. Like, you can choose a test point that is in the shaded region. And usually, like 0, 0, the origin is the easiest test point to pick as long as it's not on the boundary line. But you can choose a point that's in the shaded region, and then you're hoping for a true statement when you substitute that point into the inequality, because you're saying it's part of the solution set. But if you choose a point that's not in the shaded region, then you would be assuming that you should be getting a false statement when you substitute the point in. So in this case, if we substitute the origin, so 0, 0, oops, 0, 0. Okay, we get 0 is greater than or equal to 3. That's true. Okay, so that tells me that we would end up, for this first inequality, shading above the boundary line, which is where oh no, that's false. I'm sorry. Thinking clearly. Okay, so 0, we get 0 greater than or equal to 3. That's false. So what that tells us is that we should be shading on the side opposite of where 0, 0 is, right? 0, 0 is right here. Okay, and we can see that we end up shading on the opposite side of the boundary line. You could also, if you were testing to see if you shaded correctly, you could pick a point, like you could pick -3, 0. Substitute that into the inequality. So I said -3, 0. Okay, that is a true statement, and therefore we know that we did shade on the correct side. So you shade first. Okay, well, y is greater than, so that tells me I need to shade above the boundary line, and then you can just double check by doing a test point. Okay, so then over here, if we substitute 0, 0 in, and 0, 0 is just usually the easiest, if possible, to substitute in. We get 0 is less than or equal to 3. Well, that is a true statement. Okay, so we would expect to be shading on the side that 0, 0 is on, and we can see that that's true. So that can just confirm that you have shaded the correct side. Okay, so which of these ordered pairs solve our solution, part of the solution set to the inequality? So you can figure this out just by substituting them all in. So if we want to test -2, -1, substitute -1 in for y, -2 in for x, Okay, that's false. Okay, so therefore we know that -2, -1 is not part of the solution set. If we try 0, 0, well, that's false as well. Okay, therefore 0, 0 is not part of the solution set. Try -2, 8. Oh, this was for here. Let me move that over. Okay, 8 is greater than 6, so that's true. So -2, 8 would be part of the solution set. Okay, so you can just double check. I'm not going to do the last two. You can double check whether or not 2, 1 and 4, 2 are part of the solution set to this inequality by substituting them in. All right, so for graphing the solutions to linear inequalities, first, you're going to solve for y in the inequality. Get y by itself on one side of the inequality. So basically, the boundary line, you'll be able to see what the equation of the boundary line is in slope-intercept form. So y equals mx plus b. And then you want to determine whether or not to shade, or that your boundary line will be solid or dashed. So solid would be the less than or equal to or greater than or equal to, and then dashed would be strictly less than or strictly greater than. Okay, and then you're going to shade the half plane above the line if y is strictly greater than or y is greater than or equal to, and you'll shade the half plane below the boundary line if y is strictly less than or y is less than or equal to. And then you can just double check that your shading is correct with a test point. Okay. So for this inequality, we can see y is already by itself on one side of the inequality. So the equation of the boundary line is y equals -3x plus 1. And because this is y is strictly greater than, we know that we're going to have a dashed boundary line. So I will graph the boundary line by first graphing the y-intercept 0, 1, and then using the slope of -3 to extend the boundary line. All right, so we're using our skills from the last chapter to graph the line, and then I'm going to do my best to make it look like a straight dashed line. Okay, and then the shading is going to be above, since its y is strictly greater than. Do my best to shade it nicely. And then I'm going to choose a test point. So I'm going to choose the point 1, 1 as my test point. So I want this to give me a true statement when I substitute 1, 1 in, which I do get a true statement. So that checks that we shaded the correct side of the boundary line. Okay, in this next inequality, we need to first get y by itself on one side of the inequality. So subtracting 2x from each side, and then dividing by -5. And remember that when we divide by a negative, we need to switch the direction of the inequality. So we get y is less than or equal to 2/5 x plus 2. So our boundary line will be the equation y equals to 2/5 x plus 2, and it's going to be a solid boundary line since it's y is greater than or equal to, right? To determine the type of boundary line, we look at the inequality, the type of inequality symbol. So I'm going to graph my boundary line. So y-intercept of 0, 2, slope of 2/5, so up to right 5. Up to right 5. And then I go down to left 5 to extend. Okay, the shading, okay, looking at this inequality, so it's y is less than or equal to, so we're going to end up shading below the boundary line. And we can check, it looks like 0, 0 is in our shaded region, so I'm going to use 0, 0 as my test point, and I'm going to substitute into the original inequality just to make sure I hopefully didn't make any algebra errors. We get 0 is greater than or equal to -10, which is true, so it looks like we shaded on the correct side. Okay, this is a little bit different. So our boundary, notice y is already by itself on one side of the inequality. So our boundary line is going to be y equals to 2, which is a horizontal line. Okay, because it's y strictly less than, we're going to have a dashed boundary line. So I'll graph my dashed boundary line at y equals to 2. And then because y is less than 2, the shading will be below. Okay, 0, 0 is in that region, so we can double check with our test point that we've shaded correctly. I can only substitute the 0 in for y, and that is true. So we have shaded correctly. Okay, notice there is no y in this inequality. Think back, you know how to graph this on a number line, right? For x strictly greater than -3. Well, now that we're in 2 dimensions, our boundary line is going to be the equation x equals to -3, which is actually a vertical line. And it'll be a dashed boundary line. And then the shading, so if we think back to the number line here for this inequality, we would have shaded to the right of -3 for all values of x that are strictly greater than -3. So we're going to also shade to the right here. Oops, I don't know why I put an extra t on there. Okay, I can again use 0, 0 as a test point. Only substituting 0 in for x, and that's a true statement. Okay, so for this inequality, let's get y by itself on one side by subtracting 5x from each side of the inequality. And then we're going to divide by a -1, so we need to remember to flip the inequality. So we get y is greater than or equal to 5x minus 10. Our boundary line is going to be y equals to 5x minus 10, and it'll be a solid boundary line. So I graph my y-intercept of -10, and then go up 5, right 1, 5, right 1, up 5, right 1, up 5, right 1. Okay, and then our shading will be above, since y is greater than or equal to. And then we can do test point, 0, 0's in there. And I'm going to substitute into the original inequality. And that is a true statement. 0 is less than or equal to 10. So we have shaded the correct side of the boundary line. Okay. Getting y by itself on one side of the inequality, I'm going to subtract 2x from each side, and then we will divide by a -3, and again we need to flip the inequality this time. So we get y is less than 2/3 x minus 3. So the boundary line, the equation of the boundary line is y equals 2/3 x minus 3. Be a dashed boundary line. So the y-intercept of 0, -3, go up to right 3 for the slope. Down to left 3, down to left 3 to extend to the left. And then do my best to draw a straight dashed boundary line. Okay, shading will be below, since its y is less than. I like to, for the test point, I like to choose a point that's in the shaded region. So like, I will use, how about 0, -4 as my test point. Substituting into the original inequality, we get 12 is greater than 9. That is true. Therefore, it looks like we shaded on the correct side of the boundary line. Okay, so that's it. Eventually, we will be looking at, we'll be using this skill again to look at we'll solve word problems that require setting up a linear inequality in two variables, but then also looking at systems of linear inequalities in two variables, which there's some cool applications for those.